Hello, everyone, and welcome to Software Architecture Monday. My name is Mark Richards, and in this lesson, number 185, we'll take a look at a very interesting concept in software architecture called residuality theory. You can get a listing of all the lessons I do in Software Architecture Monday through my website at developer2architect.com/lessons. Residuality theory is a theory described by Barry O'Reilly in both videos, conference sessions, and also books about this technique within software architecture to accommodate change and uncertainty. As a matter of fact, I would encourage you to take a look at his video from a conference session in Oslo, as well as his most recently published book on residues, and I've provided the link right there. What I'd like to do in this short video is really introduce this concept of residuality theory as it applies to software architecture. Now, Barry O'Reilly does a fantastic job through academic papers, through his conferences and visuals, as well as his latest book, to really give you a solid understanding of what residuality theory is and how it can be applied. I'll show you a short introduction to this. Undoubtedly, all of us can agree that we have change and uncertainty everywhere. Change within our environments, within our technology and our platforms, within business, and certainly within the marketplace and global changes. All of this change and uncertainty causes a lot of stress in our software architectures to the point where eventually a lot of those just simply stop working. So what I'd like to do is show you some of the premises of residuality theory. So there's two basic premises within residuality theory. First is that there is no way software architects can predict all of the changes and all of the uncertainty that exists that will impact the system and its corresponding architecture now and in the future. And the second premise is that current methods of software architecture cannot capture time, uncertainty, and change. Let me show you an example of this. Part of the problem that residuality theory describes is when we create an architecture, that architecture for that system is based on static components and the interactions between those components. But this is only a snapshot in time because it's based on what is called known knowns. In other words, things we know about already and existing requirements. And this is a very traditional approach for constructing or building an architecture. However, this traditional approach does not take into account unknown unknowns. It doesn't take into account time and uncertainty and also change that we cannot predict. That's where residuality theory comes in. And so let me show you a couple of definitions. First, that initial architecture that we put together, where we do use components and their interactions, is what Barry O'Reilly calls a naive architecture, an initial starting point, a base architecture. Now we create this architecture with the understanding that it will need to change and that this complex system won't be able to predict and adapt to all sorts of conditions. Those conditions, by the way, are something called in residuality theory stressors. Now, a stressor is an unexpected or external change or event that the architecture doesn't take into account. And our response to stressors is to change the architecture to accommodate that stressor. And that change is called a residue. And that's the leftover part of the system after a system change. And the point is that those residues become part of the architecture now. As a matter of fact, these residues are in fact, through residuality theory, defined as the building blocks of software architecture. Rather than focusing on new components and interactions, we basically focus on these residues. Now let me show you an example of why this is so important. Those residues become the building blocks. And the whole idea, the whole purpose of understanding and embracing residuality theory is that over time, these residues take into account other stressors that we may not have ever thought of in our lives. But the fact that these residues working together can actually adapt that architecture to future stressors. And therefore, basically reaching what's called a point of criticality in the architecture. And that is kind of the basics of residuality theory. Barry, I'm sorry if I got all that wrong, but I think that's my understanding of the basics of this theory, which I am very excited about. So let me show you an example of this in action. Let's take a student assessment standardized testing system where students in all different grades, from 3 maybe up through 12, all go into their classroom or a testing center and basically take a true or false or multiple choice test. This test is then automatically graded and compared against students, teachers, schools, and other school districts to see how they do. And as a matter of fact, this is the architecture for part of that system. Questions from the test taker are delivered up to the student through a student user interface. The student answers a question, and that gets received by the test taker. The test taker then forwards that answer to a queue and then delivers the next question to the student. Meanwhile, the autograder dequeues that answer, compares it against a cached answer key, and marks it either correct or incorrect, and inserts it in a student answer database, which is then used for later reporting. That's the idea. And as a matter of fact, this architecture works very well, and that autograder does grade these multiple choice and true-false questions automatically. It's a pretty solid system. Until things change. Let me show you an example of a stressor. You see, the education department wants more accuracy. So to avoid guessing, the education department would like to add the capability to have short answer questions added to certain grades and certain tests. Now, these questions would have to be graded manually by teachers, and then the results, correct, incorrect, or even a new result, half credit, then inserted into that student answer database alongside all of the auto-graded answers. For example, here's a question. State 2 primary factors that led to the decline and fall of the Roman Empire. This is 1 or 2 sentences, a short answer. Turns out, our existing architecture won't accommodate this stressor. So our response is to change the architecture. And what we need to do is add another queue to be able to forward those text-based questions, the short answer, over to a queue. And then a new service to capture those text-based or short answer questions, or in this case the answers, and store them temporarily in an ungraded answer database. Then we have a manual grader. Now this service is responsible, notice we have a new UI for the teachers, to basically provide the teachers with the answers and the corresponding questions. They grade them and then send that grade down to the student answer database. Now we still have the capability of doing multiple choice and true-false questions. However, what we've done is now we've added the capability to do short answer questions. And all this change to the architecture is considered the residue. Now, what's the point of this theory? The point of this theory is this. By focusing on residues as the building blocks of our architecture, it is hoped as I mentioned before, that the combination of these residues, called attractors formally in residuality theory, will be able to handle future stressors that we never thought about. For example, here's another stressor. Based on the success of the short answer questions, the education department would now like to add the capability to have essay questions added to certain tests. Now, these questions, and of course the answers, would be graded in the same way as the short answer, but these are long, several pages long. For example, question 17, explain why it's not possible to travel faster than the speed of light. Turns out, our architecture is able to handle this stressor without a change to that architecture, because the essay question's stressor is actually handled by the residue created from the prior stressor, which was the short answer. And therefore, there might be some minimal functional changes, but the key point is no changes to the architecture. The architecture starts growing based on these building blocks, these residues. So that is residuality theory. Again, here's the link on leanpub.com/residuality theory, where you can actually view Barry O'Reilly's introduction video to residuality theory, and also his book that he just released on residues. I would encourage you to look at and also download it and purchase that book as well. This is a very fascinating theory about how to handle change, how to control time, and also uncertainty within complex systems that we all have to deal with. So this has been Lesson 185, kind of an introduction, just evangelizing Barry O'Reilly's theory about residuality and how it applies to software architecture. So stay tuned in 2 more Mondays for the next lesson in Software Architecture Monday.